The study of tidal circularization in short-period binaries has garnered significant attention in astrophysics. Observational evidence for tidal circularization was first reported by Mayer and Mermiliod, 1984, and Mathieu and Mazeh, 1988, who observed that each sample of coeval spectroscopic binaries displays a circularization cutoff period, PCUT. This cutoff period is attributed to the strong dependence of tidal interaction on binary separation and therefore on the binary period. Binaries with periods longer than PCUT retain their primordial eccentricity, while those with shorter periods are circularized. Recent studies have suggested that PCUT depends on the sample age, with older samples displaying longer PCUT values. However, utilizing the large sample of main sequence spectroscopic orbits from the Gaia Data Release 3, researchers found that PCUT does not depend on stellar age but varies with stellar temperature. Specifically, PCUT decreases linearly from 6.5 days at an effective temperature of 5700 K to 2.5 days at 6800 K. The researchers employed a new algorithm that relied on the clear upper envelopes displayed in the period-eccentricity diagrams to derive PCUT. These results contradict the theory that assumes circularization occurs during the stellar main sequence phase, a theory widely adopted by many studies. Instead, the findings suggest that circularization likely occurs during the premain sequence phase, as proposed by Zahn and Bouchet in 1989 and later by Khaluillin and Khaluillina in 2011. The weak dependence of PCUT on cluster age is not significant and may be due to the different temperatures of the samples. If true, this has far-reaching implications for the theory of binary and exoplanet circularization, synchronization, and alignment. The study utilized the unprecedentedly large sample of main sequence spectroscopic orbits from the Gaia Data Release 3 to investigate the tidal circularization of short-period binaries. This study relied on the work of Bashi et al. 2022, who confronted the Gaia orbits with the LAMOST and GALA RV databases and constructed a clean sample of 91,740 Gaia SB1 orbits. This sample served as the basis for the period-eccentricity relation. The findings of the study have significant implications for the theory of binary and exoplanet circularization, synchronization, and alignment. The results suggest that circularization occurs during the premain sequence phase, challenging the widely adopted theory that assumes circularization occurs during the stellar main sequence phase. The study highlights the importance of considering the stellar temperature in the analysis of tidal circularization in short-period binaries. Analyzing eclipsing binaries, EBs, offers a unique opportunity to study the effectiveness of tidal circularization. Unlike spectroscopic binaries, EB samples provide a cutoff ratio that distinguishes circular from eccentric orbits. In spectroscopic samples, the cutoff period is used instead. Building on previous studies that employed a piecewise asymptotic function to determine the cutoff period, the authors adopt a similar approach. They use a piecewise asymptotic function to model the upper envelope of eccentricity as a function of period for a given sample, marking the edge of the populated region in the period-eccentricity plane. The authors apply this technique to a large, cleaned Gaia sample of spectroscopic binaries, focusing on main sequence A, F, and G primaries. By dividing the sample into temperature bins and deriving the corresponding cutoff periods independently, they find a clear dependence on the stellar temperature of each bin. To obtain the best parameters of the upper envelope, the authors develop an algorithm, which they test on 6 simulated binary samples. The main result reveals a dependence of the cutoff period on the primary temperature of each subsample, inconsistent with the theory that circularization occurs during the stellar main sequence phase. The color magnitude diagram, CMD, of the clean Gaia sample of binaries is presented in Figure 1, while Figure 2 displays the period-eccentricity diagram for the main sequence reduced sample. The authors employ specific limits to identify main sequence binaries and remove orbits with unconstrained eccentricity using the Lucy and Sweeney, 1971, approach. This section of the research paper delves into an in-depth analysis of the orbital characteristics of a sample of spectroscopic binaries, SB1, focusing on the period-eccentricity diagram. The authors utilize a cleaned sample of 17,474 megasiemens SB1 systems, from which they derived the eccentricities and their corresponding uncertainties. The period-eccentricity diagram reveals a complex distribution of eccentricities, prompting the authors to examine the ratio between the derived eccentricities and their uncertainties as a function of the orbital period. This analysis yields two distinct clusters of binaries, one with shorter orbital periods and another with longer periods. Using Kamian's clustering, the authors identify the centers of these clusters and find that most binaries in the lower cluster have well-constrained eccentricities, while those in the upper cluster have unconstrained eccentricities. Applying the Lucy and Sweeney, 1971, threshold of E, delta E equals 2.45, the authors define a sample of 10,325 binaries with at least 95% confidence for non-circular eccentricity and 7,149 binaries with unconstrained eccentricities. The age-effective temperature dependence of each subsample reveals no apparent age difference between the two subsamples. The paper then shifts focus to analyzing the subsample of 10,325 binaries with well-constrained eccentricities, aiming to derive the dependence of PCUT on stellar temperature. The authors also investigate whether PCUT displays a dependence on stellar age. The period eccentricity diagram suggests that the binary eccentricities do not exhibit a clear cutoff period separating circular and eccentric binaries. Instead, the eccentricities gradually increase towards higher values. To better characterize this feature, the authors define an upper envelope as a function of period, equation 2, which has two free parameters, PCUT and tau. PCUT defines the separation between circular and eccentric orbits and the location of the upper envelope, while tau determines the slope of the envelope. The authors illustrate the role of tau by plotting the analyzed sample in the log p log 1e plane, where the upper envelope becomes a straight-line lower envelope with a slope of 1 tau. They also demonstrate that tau measures the period for which the upper envelope attains a specific eccentricity value, such as E equals 0.8. The analysis presented in this section provides a comprehensive understanding of the orbital characteristics of the SB1 sample and sets the stage for further investigation of the dependence of PCUT on stellar temperature and age. The period eccentricity diagrams for two subsamples of binaries from the MS unconstrained eccentricities and non-circular binaries are presented in Figure 4. These plots highlight distinct patterns between these subsamples. The left panel indicates that most eccentricity measurements fall within the circular binary distribution, while the non-circular binaries show significantly scattered data in terms of orbital period. In Figure 5, the age-effective temperature plots demonstrate comparable behavior across different periods. However, there is a considerable distinction in the variations observed. Unlike previous studies, this result indicates that the mass of low-mass binaries increases with age, and this variation is more pronounced for younger systems. This suggests that the relationship between age and effective temperature may be influenced by the mass of the binary system. The analysis indicates that the estimated ages are comparable to those described in previous studies, although they show greater variation. This evidence was observed in the period eccentricity diagrams and age-effective temperature plots. A key model comparison shows that there is a significant difference between the observed trends and those predicted by the model, particularly for younger systems. This difference could be attributed to the effects of mass loss on the orbital period and eccentricity of the binary system. The study also examines the effects of varying parameters on the observed trends. For instance, the right panel of Figure 4 illustrates how the number of non-circular binaries increases with age, which could be related to the higher probability of detecting these systems at younger ages. Similarly, Figure 5 demonstrates how the effective temperature varies with age, displaying a clear linear relationship for low-mass binaries. This suggests that the mass of the binary system plays a crucial role in determining its evolutionary path. Overall, the study provides new insights into the relationship between age, effective temperature, and the orbital parameters of low-mass binaries. The findings indicate that the mass of the binary system significantly influences the observed trends, particularly in younger systems. This research contributes to our understanding of the complex interplay between these factors and highlights the need for further studies to fully understand the evolution of low-mass binaries. In the context of closed binary star systems, understanding the tidal circularization process is crucial, and a key aspect of this process is the eccentricity distribution in the log period plane. To address this, the authors develop an algorithm to derive the upper envelope of this distribution, employing a probabilistic approach. They introduce a probability density function, PDF, that describes the likelihood of observing a binary with given eccentricity and period, derived from a sample of 4,430 binaries with orbital periods shorter than 30 days. Through an MCMC routine, the best fit upper envelope model is obtained, yielding parameters PCUT equals 4.67 days, tau equals 1.70, and delta equals 0.09. This model provides a statistical framework for analyzing tidal circularization. To validate their algorithm, the authors tested on simulated binary samples, utilizing simplified tidal interaction equations that govern the circularization efficacy over the binary lifetime. The results demonstrate the effectiveness of the proposed method in accurately modeling the tidal circularization process in closed binary systems, offering a robust tool for understanding the complex interplay between binary star systems and their orbital evolution. This simulation study delves into the circularization process of binary samples, focusing on the interplay between period and eccentricity. Utilizing equations 6 and 7, the authors approximate the rate of change in eccentricity and period, leading to the derivation of equation 8. This equation outlines the evolutionary trajectory in the log p plane but does not predict specific changes in eccentricity and period over time. The study employs 6 different values for the circularization parameter b, representing varying lifetimes and circularization effectiveness. Each sample consists of 500 binaries, with other simulations demonstrating that the best fit parameters obtained are independent of the number of binaries in the sample, affecting only the parameter uncertainties. The upper envelopes in Figure 7 support the approach of using an upper envelope to characterize the period-eccentricity relation. These envelopes are included in the figure along with their corresponding cutoff periods. Table 1 provides the best fit values for PCUT, tau, and delta for each of the 6 bins of circularization parameter b. Figure 8 illustrates a tight linear relationship between the cutoff period PCUT and the circularization parameter b, expressed as log PCUT equals 0.198 log b 0.231. This relationship can be traced back to equation 7, noting that for small eccentricity, the logarithmic derivative of E is approximately 1, E. The cutoff period PCUT is the period at which delta E approximately equals 1 during the lifetime of the binary, so that BP cut approximately equals 16 to the power of 3. This page highlights the novel approach of using an upper envelope to describe the period-eccentricity relation in binary samples and demonstrates the tight linear relationship between the cutoff period and the circularization parameter b. The authors investigate the relationship between the cutoff period, PCUT, and stellar effective temperature, TEF, in main sequence binaries. Analyzing 3,959 orbits from Gaia with TEF between 5,300 and 7,700 K. They divide the stellar temperatures into 18 bins and fit an upper envelope to each bin using their algorithm. The results, presented in Figure 10 and Table 2, reveal key features. PCUT decreases linearly from approximately 6.5 days to 2.5 days as TEF increases from 5,500 to 6,800 K. Following the linear model given by equation 10, where PCUT is inversely proportional to TEF. The linear fit is tight, suggesting that PCUT uncertainties are overestimated by a factor of approximately 1.7. Notably, PCUT remains flat in the ranges 7,006,800 K and 6,005,300 K. With a possible small jump at the Kraft break of 6,100 Ka. A strong correlation exists between PCUT and the tidal dissipation timescale, tau, across the 18 bins, indicating that shorter PCUT corresponds to larger tau. The upper envelope's shape reveals that all reach the same eccentricity at a period of approximately 30 days, which can be attributed to binaries with relatively long periods retaining their primordial eccentricities and showing no dependence on TEF. This finding suggests that the cutoff period is influenced by tidal interactions and stellar evolution, with implications for understanding binary star formation and evolution. The period-eccentricity relationship for 18 subsamples of MS Gaia binaries is illustrated in Figure 10. The fitted upper envelope, detailed in Table 2, is represented by the red dashed line, with the red area denoting the transition region of delta along the envelope. This correlation between orbital period and eccentricity among binary systems provides insights into their dynamical properties and potential evolutionary pathways. Notably, the variation in PCUT values across different temperature ranges indicates a complex interplay between these parameters. This interplay has significant implications for understanding the formation and stability of closed binary systems. The observed relationship suggests that the orbital period and eccentricity are closely linked, with the envelope serving as a boundary beyond which the systems are unlikely to exist. The fitted upper envelope is a critical component of this analysis, as it represents the maximum eccentricity achievable by binary systems at a given orbital period. The transition region of delta along the envelope marks a significant change in the behavior of the binary systems, with implications for their long-term evolution. The findings presented in Figure 10 and Table 2 contribute to a deeper understanding of the complex relationships between orbital period, eccentricity, and temperature in closed binary systems. These insights have important implications for the study of binary star formation and evolution, and highlight the need for further research into the interplay between these parameters. The authors delve into the relationship between the cutoff period and stellar age, aiming to establish an approximate scaling law of circularization. Figure 11 illustrates the correlation between the cutoff period, PCUT, and stellar temperature, TEF, demonstrating a strong connection. To further explore this relationship, the authors divide the age-temperature plane into evenly spaced bins and derive PCUT values for each bin. By fitting a two-dimensional function to these 14 bins, they arrive at equation 11, revealing that PCUT is significantly influenced by stellar temperature but not by stellar age. In an effort to scale the tidal interaction with stellar mass, radius, and orbital period, the authors derive a theoretical expectation for the dependence of PCUT on stellar temperature. Focusing on stars with radiative envelopes, they draw upon Zahn's work on turbulent dissipation and radiative damping. Simplifying the circularization process by considering only the eccentricity decay and disregarding the associated period change, the authors utilize equation 7, which describes the eccentricity derivative to first order in E. This equation includes a parameter, Brad, which can be adjusted to alter the circularization effectiveness. Building on Claret and Cunha's work, the authors develop an approximate scaling law of circularization, which they intend to compare with observational results. This law is crucial for understanding the interplay between tidal forces and stellar properties in shaping the orbits of closed binaries. The distribution of orbital eccentricity in spectroscopic binaries observed by Gaia is examined, with a focus on the relationship between period and eccentricity. Tidal interactions between the two stars in a binary system are thought to shape the eccentricity distribution, resulting in a characteristic upper envelope that begins at a critical period, PCUT, with zero eccentricity and increases towards higher eccentricities for longer periods. This envelope is modeled using a simple function of two parameters, PCUT and tau, and a modified Fermi function describes the probability density distribution of binaries above and below the envelope in the log p, e plane. Analysis reveals an unexpected linear decrease in PCUT with increasing stellar temperature for G and F stars, from 6.5 days at 5700 K to 2.5 days at 6800 K, with a statistically significant slope. This trend contradicts the Zahn dynamical tide theory, which predicts that PCUT should increase with temperature due to more efficient tidal circularization in radiative envelopes. The observed PCUT trend may be influenced by different primordial eccentricity and period distributions, binaries with different ages and mass ratios, and stellar temperature spreads, contributing to the uncertainty in PCUT values. The presence of both convective and radiative envelopes in the examined temperature range may attribute to the observed linear relationship between PCUT and stellar temperature. The study highlights the importance of considering alternative theories and models for tidal interactions, such as those proposed by Tassoul and Tassoul, 1997, Routard, 1992, Routard and Zahn, 1997, Mayer and Mermiliad, 1984, Zahn and Bouchet, 1989, Khaluillin and Khaluillina, 2011, Turkim and Martin, 2021, and others. Further investigations are necessary to fully understand the mechanisms driving the observed trends and reconcile them with theoretical predictions. Tidal circularization in short-period binaries is a crucial concept for understanding their evolution. Theoretical models, such as those proposed by Zahn and Bouchet, 1989, suggest that circularization occurs during the Permain sequence phase, with expected cutoff periods between 7.2 and 8.5 days. This idea is supported by the work of KK11, which provided updated Permain sequence evolutionary tracks and estimated cutoff periods for different stellar masses. Tidal circularization has significant implications for various astrophysical phenomena, including the evolution of short-period binaries, closed triple systems, cataclysmic binaries, and X-ray binaries. It also plays a crucial role in the formation and evolution of exoplanets, hot Jupiters, and their orbit alignment with the stellar spin. To further our understanding of tidal interaction in binary systems, 5 observational avenues are proposed. Firstly, analyzing other samples of spectroscopic binaries can confirm the results and investigate the dependence of the cutoff period on parameters such as mass ratio, stellar age, and metallicity. Secondly, studying samples of eclipsing binaries can accurately derive small eccentricities. Thirdly, exploring long-term tidal interaction, including synchronization and alignment of the binary with the stellar rotation, can provide valuable insights. Fourthly, investigating observed eccentric pseudo-synchronized binaries, which are undergoing strong tidal interaction, can offer further constraints on the theory. Lastly, examining the orbital decay of very close hot Jupiters can provide additional constraints on the theory of tidal interaction. These avenues can help refine our understanding of tidal circularization and its implications for various astrophysical phenomena. The research relies on high-quality data, such as the catalog produced by the NSS Group and the Gaia team, and acknowledges the contributions of various experts in the field. Binary star systems, consisting of 2 gravitationally bound stars, have garnered significant attention in the field of astrophysics due to their complex dynamics and potential for hosting exoplanets. Recent studies have shed light on the stellar evolution and interactions within these systems, providing valuable insights into their formation and stability. Research has shown that binary star systems can be broadly classified into 2 categories: detached and contact binaries. Detached binaries, where the stars do not fill their Roche lobes, exhibit distinct evolutionary paths, with each star influencing the other's evolution through tidal interactions and mass transfer. Contact binaries, on the other hand, are characterized by the stars being in physical contact, resulting in complex orbital dynamics and mass transfer. The study of binary star systems has significant implications for exoplanet detection. The presence of a companion star can impact the habitability of planets within the system, and understanding these effects is crucial for identifying potential exoplanetary candidates. Recent advances in detection methods, such as the radial velocity method and transit photometry, have enabled the discovery of numerous exoplanets in binary star systems. Key findings from recent studies include the discovery of exoplanets in highly eccentric orbits, which can be attributed to the perturbing effects of the companion star. Furthermore, research has shown that binary star systems can harbor planets with unique characteristics, such as planets with highly inclined orbits or retrograde orbits. Methodologies employed in the study of binary star systems include numerical simulations, which model the complex stellar interactions and orbital dynamics. The use of machine learning algorithms has also been explored to identify patterns in large datasets and predict the presence of exoplanets in binary star systems. Despite significant progress in the field, limitations remain. The accuracy of detection methods can be compromised by the presence of stellar variability and instrumental noise. Assumptions regarding the stellar masses and orbital parameters can also introduce uncertainties in the interpretation of results. Future work aims to address these limitations by developing more sophisticated detection methods and refining our understanding of binary star system dynamics. The continued study of these complex systems will provide valuable insights into the formation and evolution of planetary systems, ultimately informing our search for life beyond our solar system. The tidal circularization process in binary star systems plays a crucial role in the formation and evolution of exoplanets. Building on the theoretical framework developed by Zahn and Bouchet in 1989, recent studies have consistently demonstrated the importance of tidal forces in shaping the orbits of close binary systems. Research by Turkim and Papalouizou in 2021 and Turkim in 2021 has further solidified this understanding, highlighting the impact of tidal forces on the orbital evolution of close binaries. The role of tidal forces in exoplanet formation and migration is multifaceted. For instance, Wei's 2022 study suggests that tidal forces can influence the migration rates of giant planets, while Tunin et al.'s 2022 research emphasizes the impact of tidal forces on the orbital evolution of close-ane planets. Furthermore, Turner et al.'s 2021 study suggests that tidal forces may play a crucial role in the formation of hot Jupiters. Observational studies provide empirical evidence for the effects of tidal forces on exoplanet orbits. Wynn and Holman's 2005 statistical analysis of exoplanet orbits reveals a correlation between orbital period and eccentricity. Similarly, Van Allen et al.'s 2016 study demonstrates that tidal forces can lead to the circularization of orbits in close binary systems. However, the current understanding of tidal forces in exoplanet formation is not without limitations. Wu's 2005 study notes that the efficiency of tidal forces depends on the internal structure of the star, which is often poorly understood. Yi et al.'s 2020 research emphasizes the need for further investigation into the interplay between tidal forces and other orbital evolution mechanisms. Future research directions are also outlined in the paper. Zanazi and Wu's 2021 study suggests that a more detailed understanding of tidal forces could shed light on the origins of close-ane exoplanets. Zimmerman et al.'s 2017 research highlights the importance of continued observations and simulations to refine our understanding of tidal forces in binary star systems. Overall, this research underscores the significance of continued investigation into the complex and multifaceted topic of tidal forces in binary star systems.